So today we start the algebra year with Unit 1, Section A. It's going to be about inductive reasoning and describing patterns. So your notes page, or if you have a notebook, you might want to start by putting our topic today is the Unit 1A, inductive reasoning and describing patterns. And our objective, our goal for today is going to be that we're going to look to find patterns. We're going to use inductive reasoning to make conjectures, and we're going to use rules to describe numerical patterns. Now, if you're confused by some of the words in there, we're going to see those vocabulary words as we go through, and you can add the words to your vocabulary part of your note page. You don't have to put the full definition in, but at least list the words. This whole filled in notes page this whole presentation will be available to you on Classroom as well. All right, so we're going to start with the first word here that we noticed in our heading, which is inductive reasoning. So inductive reasoning is reasoning that's based on patterns that are observed. So you just notice that something is happening in a repeated pattern. We're going to talk about sequence. Now, a sequence is an ordered list of numbers or figures, and a term in a sequence would be a single number or a single figure in the list. So let's just look at a couple of examples. We're going to find a pattern. We're going to use inductive reasoning. We're going to look at this sequence, and we're going to name the next two terms. So I just want to, again, remind you that 3 is the first term, 6 is the second term, and so forth. So that's what a term in a sequence is. The 3, 6, 12, 24, on and on is the sequence. So what are the next two terms? So stop a second and figure out what those two are. You can pause the video if you need to. And then we're going to come down to the next sequence. We're going to say, what is the pattern? What is happening from the first term to the second term? We're going to describe that, same thing up here. And then we're going to find the next two terms. And then finally, down here, it's not numerical. It's days of the week. And we're going to figure out what is the pattern and then what are the next two. So what I would recommend right now is that you pause the video, and on your notes page where it says to do your kind of your work, you can go ahead and fill those in. It will help if you put the number out in front. What is the pattern? The next two, so you kind of keep your information organized on your notes page. Once you're set with those, unpause the video. We'll come back and we'll see how you did. Okay, so the first one, 3 to 6 to 12, at first I thought, well, maybe I'm adding 3, but that pattern didn't hold. But multiplying by 2 held. So if I take 24 times 2 and then 48 times 2, my pattern is times 2. That's my description. And then the next two terms would be 48 and 96. Now the next one looks like I'm multiplying by 2, but that doesn't hold from 4 to 7. But I do notice that I'm adding 1, then I'm adding 2, then I'm adding 3. And there's actually almost a pattern in the description of the pattern. So we're adding 1 more each time would be another way to say it. So we're going to add 7, which would give us 29. And then we're going to add 8, which would give us 37. So you could describe the pattern this way, or you could describe the pattern by saying that you're adding 1 more each time. Here we're skipping a day. That's the description of the pattern, and we would skip over Saturday to Sunday and then over to Tuesday. So there's some patterns, some sequences, and we used inductive reasoning to kind of figure out what was going on. Now, a conjecture is an unproven conclusion, and it's based on observations and inductive reasoning. So you come up with a thought, and that would be a conjecture. So we're going to make a conjecture about the sum of the first 30 odd numbers. And you got to understand that that could have been the first 1,000 odd numbers. That's a lot of numbers to pick up our calculator and add. So we're going to try to see if we can make a conjecture and get to this without having to add 1 plus 3 plus 5, for 30 odd numbers. So what I do is I kind of look for a little bit of structure, and I'm going to break this down into smaller pieces. So I'm going to start, there's the first. So there is adding just one odd number would be 1. Adding the first two odd numbers would be 1 plus 3, which is 4. And I do 1 plus 3 plus 5 and 1 plus 3 plus 5 plus 7. And I'm creating, you'll notice, sort of a sequence here from 1 to 4 to 9 to 16, like we just did on the previous page. Now, times 4 doesn't work and adding 3 doesn't work. So then I'm looking and asking myself, is there anything special about these numbers? Is there anything else that I could kind of see that is going on? Now, some of you might say, well, I'm adding 3 and then 5 and then 7, but that's not going to get me out to 30 without having to keep add. Is there a way I can kind of get there faster? So look at these numbers, and I want you to think, what kind of numbers are those? So I'm hoping that somebody realized that these numbers are what are called perfect squares. This is 1 squared. 4 is 2 squared. 9 is 3 squared, and 16 is 4 squared. So those are perfect squares. Oh my goodness, that is extremely helpful, because now if I want to add the first 30 numbers, I can use inductive reasoning, and I can say, you know what? It's going to be 30 squared. So the first was 1 squared, the first 2 was 2 squared, the first 3 was 3 squared. So the first 30 numbers would be 30 squared, or 900. So now, can you make a conjecture? What would the sum of the first 35 odd numbers be? If you need to pause for a second, grab your calculator, whatever you need to do. Did you get 35 squared? Which is 1,225. Pretty cool. I now could do any number that I choose, 30, 35, 1,000 of the first odd numbers. Now, to test a conjecture has to prove true for every possible set of circumstances. If you can find one example that proves your conjecture not true, that's called a counterexample, then your conjecture is not true. So let's say some kid is learning about positive and negative numbers, maybe in 7th grade, and that person comes up and says, you know what? I think that every time you add a positive and a negative number, you're always going to get a positive number. All you have to do is come up with one example of a positive and a negative that don't add to a positive number, and that would be a counterexample, and then your conjecture wouldn't be true. Can you think of an example right now of a counterexample that would not hold this conjecture true? What is it? Okay, let me give you my example. I say this isn't true because look at this example. If the negative number is bigger than the positive number when you're adding, you're always going to get a negative. So this conjecture, you would tell this 7th grader, whoa, this is not a good conjecture. One counterexample, it's not good. So now let's just take another example of maybe a 3rd grader learning multiplication, and you give them this table, and they're learning how to multiply by 5, and they're so incredibly excited when they look at this because they see kind of a pattern. What I want you to do right now is to pause the video, and I want, in block A here, I want you to think of what would be a conjecture that would be true about multiplying by 5, and what might be a conjecture that is false if you're that 3rd grader looking here. Come up with a true conjecture and one that is false. And of course, if it's false, all you need is one counterexample to prove it false. So I'm going to ask you to pause the video, take a minute to come up with those, and write it on your notes page for problem number 6. Okay, now that you're back, what would be an example of, I'm going to actually start with the false one. If I was a 3rd grader and I was looking at all these, I'd be like, cool. Every time I multiply by 5, the end of the number that I get, the product, will always end with a 5. That's what a 3rd grader might think. But you know that a counterexample was be, sure, that works if you're multiplying by an odd number, but if you multiply by any even, you're not going to get a number that ends in 5. So this conjecture is not true. So a true conjecture might be that if 5 is one of the factors and an odd number is the other factor, then the product would end in 5. So there's an example of coming up with conjectures and providing counterexamples. And so let's take this out to the real world. Here's a graph. Now, notice how important it is to have the title, because if we didn't have the title, we would realize that we're talking about months, January, February, March, April, May, June. I see that this is the number of something sold, but boy, is that title important, not to mention these great pictures, but it's the number of skateboards sold. So notice in January, and then in February, and then in March, and notice it's almost linear. There seems to be a line and it's decreasing, it's going down. So just take a look at this and let's look at the next slide. And it says, what do you observe from the graph? So number 7, make a conjecture about what you think, how many number of skateboards will this store sell in June? So if we come back, this would be June. What number would you think it would be? So pause the video and kind of come up with what you think that number might be. Okay, you're back. So, it looks like we're dropping kind of by, it would be about 42 because it looks like we're dropping by about 3 skateboards per month. Now, what would happen in July? Make a conjecture about July. Again, pause for a second. And then start the video up again. Just kind of get used to doing that for yourself so you have the right amount of time to do the thinking. Okay, hopefully you're back. So if you, just follow this graph, you would make a conjecture that there were 39 skateboards going to be sold in July. But wait a minute. Let's think about that in the real world. What would happen kind of in June, July? Would this pattern continue? I'm thinking, wait a minute, wouldn't you sell more in summer? Wouldn't kids be skateboarding outside more in the summer? So I'm kind of questioning as to whether this pattern would continue in a real world example. And how confident would you be if you use this graph to continue all the way out and talk about sales in December? What do you think about December? Stop for a second and tell me, in a few words on your notes page, what do you think would happen in December? Would this trend continue then? Well, my thoughts are, I don't think so because of holiday sales. Would they sell more in regards to the holidays that come up in those winter months? So let's talk again about some problem solving using patterns. When solving a problem and it requires a lot of steps, it's often easier to kind of break the problem down and solve a simpler problem first. We did that back a few slides ago when we did the adding the first 30 odd numbers. And so we're going to kind of look at that again. And we're going to look for a pattern. So we're going to see if we can use the pattern to solve the original problem. So imagine number 10 here. If the question was, what is the sum of the cubes? So when we talk about cubes, we're taking a number and raising it to the 3rd power. And if you look down below, we're talking about like 1 to the 3rd, 2 to the 3rd. Sum, we're going to add the first 25 counting numbers or natural numbers. So that's 1, 2, 3, 4, 5, 6. Okay. So there is the first cubed. There is the first cube plus the second number cubed and so forth here. Now, remember that when you're raising to an exponent, right, that is easy with the number 1. 1 to the 3rd is 1. And here we would have the 1 again, but be careful. 2 to the 3rd. Stop yourself for a second and think about what that is. Can you think of the mistake that a lot of people make? Yeah, so there is a very common mistake. So first of all, it's 1 plus 8, not 6. You don't just take 2 times 3. You're taking 2 times 2 times 2. 3 factors multiplied. 2 times 2 is 4, times another 2 would be 8. So just realize that a common mistake would be to put 6 here, and that would mess you up for sure. So 1 plus 8 is 9. Now this would be 1 plus 8. Now 3 to the 3rd, careful, is not 9. It's 3 times 3, which is 9, times 3, which is 27. And there is a button on the calculator, your exponent button. We'll be talking more about that as we go along. And then we come down here, we're going to have the 1 plus the 8 plus the 27, and 4 to the third is 64. So now if we look at these numbers, 1 and 9 and 36 and 100, I happen to be noticing again that these are what are called perfect squares. This is 1 squared. This is 3 squared. That is 6 squared. This is 10 squared. But the question is, where does the 1, the 3, the 6, and the 10 come from out of this list? So can you find a 3? Well, look at 1 and 2. Can you find a 6? Look at the 1, the 2, and the 3. Can you find a 10? 1 plus 2 plus 3 plus 4. Notice that each time, if I add the bases here, 1 plus 2 is 3 plus 3 is 6, and then square it, I'm getting the sum of the cubes. Let me show you what that looks like. So to get the 25, now this isn't simple, but all I need to do is add 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to 25. I need to add that and then square it. Kind of easier to do on a calculator than to take 1 cubed plus 2 cubed plus 3 cubed. It's actually a faster operation. So 1 plus 2 plus 3 plus 4 up to 25, and then square it. You're going to take 325 and square it. And the first 25 cubes added together are 105,625. Again, taking the bigger problem, breaking it into a smaller piece, and what can I notice about the results of what's happening there? Okay, so we're going to just add a few more vocab words to our list, and we're going to end with these 2 ideas today. A couple more slides just showing you what these are. So a recursive rule versus an explicit rule. What we've been talking about up to this point in time are recursive rules, adding 2, multiplying by 3. They're words to describe a pattern, but in order to continue the pattern, you need to know the term before the one that you are looking for. So if you want the 10th term and you're adding 2, you need to know what was in the 9th term to add the 2. So if you start with the number 3 and you add 2, then you would go to 5, and then you would add 2, and you go to 7, and you go to 9. If I ask you all to write a sequence that has the recursive rule of adding 2, and that's all I say, you could all have different sequences. So somebody could have 2, 4, 6, 8, but somebody else could start with 1,000, 1,002, 1,004, and get a different sequence. So you need to know what the term is before, and you have to get out to the 100th term, you got to keep adding 2 out 100 times to get out to that, or 99 times to get out to that 100th term. There's a different kind of a rule called an explicit rule. An explicit rule, explicit means it's out there, right out in front. You can get right to the 100th term or the 1,000th term. You don't have to keep adding 99 times. You can get right to the 100th. It's usually kind of like a formula. We're going to call it a function rule, but a description or a formula of a pattern or sequence that allows you to obtain any term directly. So here's an example. We're going to be talking about this in a couple of days. This is called function notation. If you don't remember it or it's not something in your toolbox, we're going to be talking more about it. This could have just been another variable. Just think of it as a variable. This is the output variable. The input variable is n, and we can see that input variable over here. So n is going to represent the number of the sequence. So if I was to I want the first term of the sequence, I would let n be 1. 2 times 1 is 2. Take away 3 would be -1, and my first term would be -1. But what if I want to know what the 12th term is? So I want the 12th term. See how I put the 12 in there? I want the 12th term of the sequence. So I'm going to take 2 times the term number and subtract 3. 2 times 12, order of operations, we're going to multiply before we subtract. We get 24, take away 3, and the 12th term is 21. If I want to know what the 100th term is, I take 2 times 100, which is 200, take away 3, it's 197. You can find, using an explicit rule, any term in the sequence directly without having to keep like adding 2 or subtracting 3 or multiplying by 4, you can get directly out to that term. That's called an explicit rule. So let's take a look at this sequence. What is the recursive rule? It's basically another word for what's the pattern. So 6 to 12 to 18 to 24 to 30, the pattern would be that we're adding 6. That's the recursive rule. I'm adding 6 to the previous term. Now, if I wanted to get out to the 60th term, I really don't want to add 6 until I get out to term number 60. So the next question is, how would you find the next two terms? Well, I would add 6 and I would add 6, right? Like we did on the first slide today. But I don't want to do that out to, get to the 60th term. So do you notice anything? I'm going to draw your attention back to the sequence. This is the first term. This is the second term. This is the third term. This is the fourth term. This is the fifth term. 1, 2, 3, 4, 5. Do you notice anything about each, term? Can you tell me what the 60th term is? So I'm going to let you pause and think about that and come back when you're ready to go. So the 60th term, did you notice it would just be 6 times 60? Because the first term is 6 times 1. The second term is 6 times 2. The third term is 6 times 3. So if I just take 6 times 60, I would get out to this, 60th term without having to keep, adding 6 over and over. What would the nth term be? So I want to put a variable in there so I can do it, and have a kind of more of an explicit rule. It would be 6 times n. So the n would get replaced by whatever term number I want. And that would be an explicit rule, which is AKA, also known as an explicit function. This rule allows you to directly determine any term in the sequence without having to keep doing something over and over again. So now when we try this one, I'm thinking that I'm going to add 10, and that failed. I don't know. So is there something I could multiply by that would hold through? What I'm going to ask you right now is to pause the video and look, and what would I need to multiply by to get maybe this sequence to work? Come back when you're ready to go. Now, if you couldn't find it, let me give you a piece of advice. Try something. Take this term and divide it by that term. Take this term and divide it by that term. Take this term and divide it. Do you see the same number coming up? And if you do, kind of in reverse, that would be what you would have to multiply. Did you get that you're multiplying by 1.1? Good job if you did. Now, when you're multiplying, we are not quite ready right now to be able to come up with an explicit rule. We will in a few sections. So right now, we're going to have to say more on this later. That requires an exponential function. So that is our first section. We've been talking about patterns. We've been talking about conjectures, counterexamples, recursive rules, explicit rules, some of those ideas. You are welcome to, of course, at any point look back over this if you need to. And the notes page that shows all the filled in answers will also be available in Classroom, so you can refer back to it as well. Basically, what you're going to need to do is come to class with any questions. We'll do some practice together, a couple examples, and then you'll be practicing in class using these ideas. Guys, I hope you have a great day. Take care, and I'll see you soon.